Okay, we're going to continue our discussion on logarithms. Section 4.3, properties of logarithms. Now in the previous section, section 2, we started to do our work on logarithms, where this is just a continuation on it. But you got to remember the things that we already talked about, the properties we already had, which is log base b of b is 1, that when the base and the argument match, the logarithm value is 1. Because remember, these are just exponents. And so what this is saying, if we cover up part of it, so what that's saying just right there, log base b of b, it's saying what is the exponent necessary to turn b into b? B to the what equals b? Well, b to the first equals b. So that's why it's 1. Remember, logarithms are just exponents. So when the base and the argument match, the answer is always going to be 1, because what the question is asking, what that is asking is b to the what equals b? B to what exponent equals b? Well, that has to be an exponent of 1. Similarly, we already know this, log base b of 1 is 0. So what that is saying is the logarithm of 1, regardless what type of log is, log base b, common log, log, natural log, the log of 1 is 0. And again, it makes perfect sense if we remember logarithms equal exponents. So what this expression right here is asking us, b to what power equals 1? What exponent do I need to put on b to give me an answer of 1? Well, b to the 0 equals 1. So those are two properties we already have. Then what we finished up pretty much in last section, the inverse properties. That logarithmic functions and exponential functions are inverse as long as they have the same base. So that when I compose them, when I put one inside the other, because they're inverses, they quote-unquote cancel. They undo each other. So as long as you have this same base, logarithm base b, exponential base b, when I have those matching bases and I've composed them, I put one function inside the other, I put that b to the x inside the function log base b, because they're inverses, I get x. Then two specific examples. Remember, if a base is not written, it's understood to be 10. So this is log base 10 of 10 to the x is x. And then really importantly, because this is going to creep up a lot in your future life, well, not a lot in your future life, but if you do mathematics and if you go on to calculus, this is going to creep up a lot. Natural log of e to the x is x. Again, because natural logs, which are log base e, and the natural exponential, which is base e, they have the same base, they're inverses, so we get just x. And if we flip it around, b raised to log base b of x, again, note we have those matching bases, and then because logarithms and exponential functions are inverses when they have the same base, we get just that x. Then two specific examples, 10 raised to log x. If a base is not written, it's understood to be 10, so we have the matching bases again, so I get x. And e to the natural log of x is x. So evaluate the following one of these without a calculator. So the idea here is going to be to try to use this concept here of matching bases. And so what I'm going to note here on this first one is that I can rewrite 16 as, just lost my train of thought, 2 to the 4th. And now I have those matching bases. And because logarithms and exponentials are inverses, that's just going to be 4. Then here it's absolutely direct. We've got those matching bases. And because I have matching bases, because they're inverses, I'm just going to get that 10. Here, if we can remember that, natural log of e to the x is x, or in this case my x value would be 3. And if we need to see it more in action, remember that a natural log is base e. So again, we have those matching bases, and so we will just get 3. But you really do just want to remember, of course you want to remember that natural log is base e, but you just really want to learn when you see the natural log of e, natural logs, natural exponentials, or inverses, and in this case we just get the 3. And then really almost the same idea here. But again, just emphasizing that if a base isn't written, it's understood to be 10. Then I have those matching bases. And because logarithms and exponentials are inverses, in this case, I just get 4. Okay, so that's a little review of some stuff we did in the previous section. So moving on to some new properties. Now we introduce the remaining properties. The product rule for logarithms. Now let me make a little disclaimer. We always have some people in college algebra who really should be in a much higher level math class, maybe already had calculus. If you've had calculus, do not get the product rule and quotient rule and power rule for logarithms confused with anything that has to do with calculus. These are algebraic properties for logarithms. Yes, they have a similar name to a property in calculus, but this isn't a calculus class. So these are just algebraic properties. So the product rule for logarithms, it says in symbols, log base b of m times n equals log base b of m plus log base b of n. In words, the log of a product is the sum of the logs, or in way less technical languages, you may split up multiplication by addition. That here we have a log of a product, m times n, and we can split that up by saying log m plus log n. And it's true for all bases. So an example here, log of 3xy, that's all just multiplication. So I can split that up by addition to log 3 plus log x plus log 7. There's a typo. That should be a y. And like I've said when we found other typos, I will get around to fixing the typos someday, but frankly, they're never going to get fixed in these videos. They will eventually get fixed in the notes, but they're never getting fixed in these videos. Number 6, the quotient rule for logarithms. Log base b of m over n is log base b of m minus log base b of n. In words, the log of a quotient is the difference of the logs, or in way less technical words, you may split up a fraction by subtraction. So an example here, natural log of 4 over x is natural log of 4 minus the natural log of, God, there's another typo. This should be an x. Guess I just wasn't careful enough when I was typing up these notes. But the point here that the natural log, or any logarithm, but here we have a natural log, the log of a quotient can be split up by subtraction. So this should be natural log of 4 minus the natural log of x. 7, the power rule for logarithms. Log base b of m to the p equals p log base b of m. In words, an exponent on the argument of the logarithm, and very importantly, and only on the argument, may become a coefficient in front of the log. So log base 3 of x to the 5th, and then just for emphasis sake, depending on the textbook or the author, sometimes they'll put the argument in parentheses, sometimes not. You just have to get used to both ways. But here we want to remember one really important thing. An exponent applies to the one symbol to which it's adjacent. So that 5 applies only to the x. That 5 applies only to that argument x. It doesn't apply to the entire logarithm expression. An exponent applies to the one symbol to which it's adjacent. So here I just put it in parentheses to emphasize that that 5 is applying only to the x. But then my power rule says that since I have an exponent just on that argument can come down in front and become a coefficient. So log base 3 of x to the 5th is the same thing as 5 log base 3 of x. So those are the rules we have. Now rules that we don't have, down here. A common mistake that students make when it comes to logarithms is to make up rules of their own. There are no properties or rules for the following. Log base b of n plus n, addition within the logarithm. The rule that we have up here that had involved addition was addition between two separate logarithms. And if we use that rule backwards, addition between two separate logarithms can be put together by multiplication of the arguments. But we don't have a rule for subtraction within a logarithm, or addition within a logarithm. Similarly, we do not have a rule for subtraction within a logarithm. If we go back up here, the rule that we have that talks a little bit about subtraction is subtraction between two logarithms, not within a logarithm. And if we use this rule backwards, subtraction between two logarithms can be put back together by division or by making a fraction of the arguments. We have no rule that talks about the product of two separate logarithms. What we have that talks about the product is a log of a product, not the product of two separate logs. And we don't have a rule that talks about the quotient of two separate logs. When we have a fraction one here, the quotient rule up here, the fractions just are the arguments, not of two separate logs. And oh my God, these guys do not cancel right here. Huge common mistake. People will just cancel out the LOGs. No. Completely wrong. There is no way, nothing you can do with that. And then lastly, we do not have a rule for when the exponent applies to the entire logarithm. The rule we have talks about when the exponent applies just to the argument. So up in here, just to the x. If the exponent applies to the entire logarithm, there's no property for that. So as it says down here, when confronted with any of the above situations, there's nothing that can be done to simplify the expression. That if you encounter these guys and you were told to simplify, you'd be done. There's nothing else you can do. So this means, for example, that the natural log of 2 plus x does not equal the natural log of 2 plus the natural log of x. Totally not true. You can't distribute the ln. It's not a number. It's a function. Functions don't distribute. And completely and totally wrong, log 4 over log 5 is not 4/5. Again, you can't cancel it because that LOG is not a number. And this is one of the reasons why I use the word canceling all the time, because students use the word canceling. But what canceling is really, when we're dealing with fractions, is it's division. And so when you have, 4 over 4, that's 4 divided by 4, which is 1, which is why things can seem to go away, because when we're dividing and you get 1, it doesn't really change things. Those can't cancel because these aren't numbers, they're functions, and you can't treat them as numbers. Now what we're going to do with these, and our examples here in just a few minutes, what we're going to do with the product rule, quotient rule, and logarithms, we primarily use them to expand and condense logarithmic expressions, which is something we're going to need to be able to do, especially the condensing part. We're going to need to be able to condense these things in order to solve some logarithm equations. And for those of you that go on to calculus, the ability to expand a logarithm takes a problem that might be really hard in calculus and takes it to something that can be easy to deal with in calculus. And we'll do those sort of problems, not calculus problems, but expand and condense problems in the next video.